The U.S. healthcare expenditures for 1970 through 2008 are shown in the table, and a scatter plot of the data is also shown on the right. Notice in the scatter plot that the horizontal axis is the years since 1970. And so we're going to add another column to the table to represent T, the years since 1970. And so we start out with 0, 10, 15, 17, 20, 22, 24, 26, 28, 30, 31, and 38. Those values for T are going to be stored in the graphing calculator in list 1, and the healthcare expenditures, or E, are going to be stored in list 2. Let's return to the scatter plot and see that it does suggest that we may have an exponential function with a base greater than 1, since the scatter plot is suggesting that we may have the horizontal asymptote and the curve is concave up, moving up with an increasing slope. However, we've seen that power functions can have the same appear to have the same behavior over a short set of x values. So what we are going to do is we're going to graph t versus the natural log of e. And if that is linear, that is confirmation that the original data is exponential. If it is linear, we will then proceed to find the equation of the regression line and then manipulate that using our properties for logs and exponentials to get an equation of t and the original expenditure data. So let's proceed by going to the graphing calculator, and I have already stored in the graphing calculator the data in L1 and L2. And so we'll proceed now to put the data for the natural log of the expenditures into the third list, or L3. So I'm going to use the arrow keys to put the cursor in the L3 cell, and then I'm going to press natural log second 2. And you will see that what that does is display the function natural log of L sub 2. That is the list containing the E values. When I hit enter, the natural log of each of the entries in L sub 2 is copied into the same entry in L sub 3. So now we're going to go back and work on creating a scatter plot of L1 versus L3. So the first thing I'm going to do is I'm going to do second y equals, which activates the stat plots. I'm going to press 1 to go to stat plot 1. It's already open from our previous work, but notice that the data for the stat plot 1 is using L1 as its x values and L2 as its y values. And so beside y list, I am going to enter L sub 3 by pressing second 3. Now the data is coming from L1 and L3. Now we also want to make sure that we have no previous functions stored in the y equal area, and so if you do, clear those out, and we'll reset the window to match our data, for which the lowest value of t is 0. So we'll have x min 0. We'll have x max 45. And we'll let the x scale be 10. Now, in terms of our y data, we took the natural logs of positive values for the expenditure, so we will set the y min equal to 0, and the largest value in L sub 2 was 2400, and the natural log of 2400 is less than 10, so we'll actually leave 10 as the y max and 1 as the y scale. At this point, I think we're ready to graph the scatter plot, so I'll press graph. And the data does appear to be quite linear. So we'll proceed with the assumption that the L1 versus L2 data is exponential, and we'll find the linear regression equation for L1 versus L3. So I'm going to go to Stat and Calc and 4 for linear regression, but this time I must enter L1 and L3 because the default is L1 and L2. So first of all, after the linear regression command, I'm going to enter second 1 for L1. Then I have to enter a comma, which is on your black keys, and then second L3. Then press enter, and here is our regression, linear regression information with the slope of the line being approximately 0.088 and the y-intercept approximately 4.619. To graph that, I go back to the y equal screen and paste the regression equation from the variables. And so I find the var key, go down to 5 for statistics, over to the EQ menu, and press 1 for the regression equation. Then when I graph, the regression equation appears on top of the stat plot. So now we have the data that we need from the graphing calculator, and we'll return back to the other screen. So now we're going to get the regression, write the regression equation in terms of the natural log of e and t. So it's going to be 0.088t plus 4.619, taking the values for A and B that we saw in the regression equation for L1 versus L3. Now we're going to use this result to get an exponential function of E versus t. So since we want the e to be alone, we're going to raise each side of the equation to, or we're going to exponentiate base e, lowercase e, both sides of the equation. So we have e to the ln capital E, representing the expenditures, equals e to the 0.088t plus 4.619. And we know that e to the power m plus n equals e to the m times e to the n. And so we're going to rewrite this as e to the ln e, which is e, is equal to e to the 0.088t times e to the 4.619. We also have the rule that e to the m times n is equal to e to the m all to the n power. And so I'm going to insert parentheses around the e to the 0.088 and raise that to the t power. Now I'm going to use the calculator and determine that e to the 0.088 is actually 1.092. And e to the 4.619 is 101.353. And that almost looks like an exponential equation, but we'll interchange the factors so that we have 101.353 times 1.092 to the t. And this is the exponential relationship between the expenditure and the time since 1970.